My name's Phil Gardiner. I'm here from Melbourne, Australia, which is, down the bottom of the map there. But this project is actually one we designed for Darwin, which is a sort of totally different paradigm. And to try and give you some ideas of where Darwin actually lives, top of Australia, it's 4.5 hours flying time from my hometown, very similar flying time from Sydney and Brisbane, the other major cities that people tend to know about in Australia. It's only about an hour out of Singapore, out of Indonesia, a couple of hours out of Singapore, and about 6 out of southern China. So it's quite an Asian city. It's quite remote. Population at the moment is only 140,000 people, so it's only just in the top 20 of Australian cities. And it's what you would call a frontier town, driven very much by mining and resource activity, agribusiness, tourism, and a big military presence, including at the moment I think about 6,000 Marines in a base an hour or so out of Darwin. So why modular? At the time of commencing this project, Darwin was in the middle of a construction boom. And there was a serious, significant shortage of accommodation, predominantly driven by a big population of fly-in, fly-out contractors for constructing a large gas plant, thousands of workers on site. The actual conditions on that site were pretty good for labourers too. The guy that stood out the front of the site with the stop-go sign was earning about $1,000 a week, which is about double what a labourer was getting on a construction site at that time. So trying to attract people to work on construction sites was pretty tough. This particular tower, which is 29 levels with a couple of basements as well, 30 levels plus a couple of basements, had been planned earlier. It had received all its planning permits and had been 90% pre-sold off the plan, is the term we use in Australia. At this point, when the decision was made to change it to a volumetric modular solution. So we were starting with a whole lot of criteria that we had to lock into that you don't normally have to with a modular design solution. You should work the other way and design a building that works around the modular system. Another important condition when designing in Darwin is it has very difficult foundation conditions. There's a thin crust of soft rock across the town, and that's underlain by sort of never-ending Cretaceous sedimentary deposits that are quite soft, unsuitable to be piled in. So you pretty much have to found in that soft rock at the top. So this was only the third building of this height, around 30 storeys in Darwin. The other two were conventional. We did the first one, and they're typically always founded on a raft foundation. But there's a limit on capacity so that you're not settling the underlying soft deposits of about 500 kPa, and to some extent that sort of puts a limit on the gross weight and the height of your building that you can achieve. So for this, we thought, a lighter construction methodology such as volumetric modular might have some other advantages as well. The other constraints in Darwin, there's a planning height of 90 metres. That's been in place since, I think they tell me, the First World War. It was driven by early aviation controls, but it's something that stayed on the statute books until quite recently. So the shipping and handling and lifting system on the modules that we came up with, which you can see a bit of an exploded view there, based on lifting from 8 perimeter steel columns. They are temporary columns. The final columns are a concrete in situ column, which you'll see a little later. But those columns also have the purpose of being able to stack 4 high in the factory and up to 2 high on board ship. These were manufactured in Ningbo, China. The models were all designed to comply with Australian building codes and standards, and that involves sending people to China to monitor the quality of the workmanship and certify installation of plumbing, electrical installations, waterproofing, and other things that we have to sign off on. So as I said, we started off with a steel-framed solution, thinking that was going to be lighter. It's, I guess, what we'd seen typically, and even as just David presented, what the typical modules you buy in the market are. But there were no existing systems on the market that would deliver 22 levels of modules. We came up with our own sketch designs and even got to the point of the developer and who was also the contractor for the job, put some prototypes into manufacture. We developed up all the details to achieve the fire rating and acoustic separation required. For Australia, we're talking about a 90-minute fire rating for structure and 60 minutes separation between units. We went right through that process, but at the end of the day, it was found to be the steel solution just wasn't working. Each compartment, by the way, each apartment on this job consisted of 2 modules, each measuring 10 metres long. One module was 4.2 wide, and the other one was 3.9 wide. With our constraint on the building already been planned and sold, we're at our 90 metres. We were limited to a 3 metre floor-to-floor height. There's very little room for servicing, and with a steel frame module, your interstitial structure depths get a little higher, and also modules at 4.2 metres wide, wider than the shipping container that David spoke about, sitting on typically a truck that's 2.4 metres wide, also created an issue. And establishing a production facility that would make these modules that would go to 29 levels was also not possible in the time. There was another constraint here too. Darwin, as you can see here on the map, if you put it in context, it's on the same latitude south of the equator as Lima. If you put it north of the equator, it's San Jose, Caracas, Bangkok. Very hot, tropical, humid climates. There was an issue there that one of the problems that had been perceived with steel modules is that if you get cooler interstitial spaces and a lot of humidity, that you can get some serious condensation problems. Even conventional apartments in Darwin already have that problem. The guys that fly in and fly out who aren't paying any power bills might go home for a week. They might leave the air conditioning running on, cold setting the whole time they're away. The actual structure and all the walls and everything else can cool down over a week. And if you've got cold exposed steel frames in cavities that are getting natural air, which is sitting up at 95 to 100% humidity, over a 30-storey building we were envisaging waterfalls. So we did look at ways to limit the amount of steel in the building. We're also looking at ways to limit the number of components that you need to manufacture a module. So in the end, we developed a concrete system which I guess is totally counter to what most people have done with modules. It's a slab and beam solution. You can, sorry, it's come up a little bit fuzzy, but each one of those rectangles is effectively a single module. You see them all, that's a ceiling plan. You see them all on the floor plate here with slabs and beams. Slabs and beams for a couple of reasons. That gave us the minimum structural weight, but also they were being manufactured in China. If I go back, Ningbo sits just south of Shanghai, just west off the tip of Japan there. We were using an unskilled workforce, effectively making these in a shed without any serious production, production lines or anything else. So the concrete was used for a number of reasons. One, it was simple to build. One, we could set up and do it in the shortest possible time. Also, with that cross-beam arrangement, we could sit them on a truck without the need for spreader frames. Again, as David mentioned, the logistics for these is a problem. So these had to go on a truck from the factory to the port. They then had to go on a ship. They then had to go on another truck. They were picked up by a crane in the factory, a crane at the port in China, a different crane on the ship, another crane at the port in Darwin, and then a different crane again on site. And you had to have systems that worked for all of those logistics and all of the regulations that happened in those different jurisdictions to allow you to do that. So we went for the concrete with the cross beams to make the job simpler again for an unskilled workforce. They were all poured on steel frames, steel forms upside down. So the top surface of the slab was cast down. The forms had all the set downs, shower wastes, everything else preset in position so that nothing could go wrong. They were then flipped over and worked their way through the factory with the attachment of the steel frames and cast-in fitments and ferrules and other things like that. So some of the details of how these things went together are shown here, what you're looking at here is a ceiling plan of a typical module. I should have elaborated on the previous page that the ceiling framing is lightweight, but we have a concrete ring beam around the perimeter. Again, because we're pouring concrete columns in situ, it was much easier if all of our load transfers occurred between concrete to concrete elements. What that also meant that all the serious structural load-bearing paths were through those concrete elements, and that meant that all of our steelwork in the permanent condition became non-structural and only required a 60-minute fire rating rather than 90, saved us on a sheet of fire-rated drywall. So the columns, that's actually the junction line between two modules down the centre. You put the two modules together and the reinforcement cages were placed on site and concrete poured. An exaggerated view of one of the ceiling ring beams here. They were also then used to act as corbels to support precast corridor slabs and to support the floor slab of the module above. Wherever possible, we tried to get everything to work for a dual purpose. So one of the things with Darwin that I didn't explain, being cyclonic, the average facade pressures we're dealing with 7 kPa, so that's about 150 pounds a square foot. Peak pressures, local pressures on facades are 13.5 kPa, so getting close to 300 pounds a square foot. Very high loads, and you also run the serious risk, particularly at the lower levels, of penetration of facades by flying debris. So all your internal partitions also have to be able to deal with that sort of explosive case of a window being blown out and getting those massive wind pressures internally as well. That tends to drive you to have fairly serious steel stud walls for your drywall anyway, and because they are quite serious to deal with those sort of wind pressures, they're also quite serious enough to allow that 4-high stacking and those other things. So we tried not to put other materials in to make the logistics work. We tried to make work the structure that we were going to have anyway to make this happen. The other advantages of the concrete floor was the building had been pre-sold as a concrete framed building. There is an expectation that you will have concrete in that marketplace in Darwin. Typically, because of the humidity, you don't have carpets. Floors are nearly always tiled. We did find with the hotel floors on the top 11 floors of this that the upside down cast floors, the finish was so good that we actually deleted the tiles and just went to polished concrete, and it was quite a good look in the end. And the other strong selling point we found with concrete is one of the difficulties, certainly in Australia, people have with modular is getting finance. The banks are very, very nervous. They're nervous of tin boxes shipped out of China. When it could be described that once this building was finished, it was really no different to a precast concrete or even an in situ concrete frame building in its structure. There was a lot more comfort given to that. So we do have steel frames around the outside to support the drywall, and that they were protected with an external skin for transport, which was effectively just the cheapest flat metal sheeting cladding that could be found. But inside all of that, first of all, the stonework was sprayed with a PU insulation in the factory, and that also added to the acoustic separation, solved some of those condensation problems, and even gave a little bit of extra structural rigidity. Water tightness during transport turned out to be one of our issues that we had to work on improving. The first shipload that came to Australia went through 3 typhoons, so we were very pleased to see that they arrived with no structural damage. I think there was only 2 or 3. Had a little bit of plasterboard cracking, an air conditioner fell off a wall, but there had obviously been water penetration, salt water penetration. There was rust stains coming off the bottom of steel stud and whatever, so a little bit of repair work had to be done. So waterproofing for above decks transport, if you're doing that on ships, is a real issue. We actually, just to be sure, for the rest of the job, changed to all below decks shipping. So again, we've gone to steel, so we're a lot heavier than we've gone to concrete, we're a lot heavier than a typical steel-framed module. They would be typically targeting that 10 to 12 tonne range. We were targeting a weight of 22 tonnes. We were achieving that by using a lightweight concrete. We started off hoping to get 1,600 kilograms a cubic metre using a expanded shale aggregate. We had a batching plant set up on site, so that, at the factory in China, so we could control that quality. We just couldn't get strength. We were getting about 10 MPa only at 1,600 kilograms per cubic metre, no matter what we did. We ended up having to push that up to about 1,800. And that extra 200 allowed us to get good structural strength. But what that's done is it's ultimately pushed the weight of the modules up to 26 tonnes. Now, 26 tonnes wasn't a problem for the cranes. 2 cranes in the factory picked that up fine. All the shipping cranes are used to handling 40-tonne containers. That wasn't a problem either. But once we got to site, that 26 tonnes proved to be a little bit of a challenge. The furthest lift for the module in the corner position, I was standing on site when that one was being lifted in, and the crane got about 5 times, got to within a metre, and the limit switches went off, and we couldn't get it into place. So a quick redesign. We had to drop it back down on the street and redesign some new rigging to go from chains to fabric slings. Fortunately, there were some in town. We managed to pull 800 kgs off the rigging, and that was enough to allow us to get them into position. As you can see, those modules, they're fully shrink wrapped in plastic as well, to also try and improve their transport conditions. Regardless of that, as I said, in the typhoon, there was still a little bit of water damage. So they were all positioned on site, as I said, with minor or no defects. The only ones that really hit town with any defects from transport were the ones that hit the typhoon. Defects out of the factory in China, that was another matter, and there certainly needed to be quite a bit of training gone in before that all of those issues could be solved. So the other difference with this system, I guess, with the in-situ poured columns is we're not constrained by the sort of tolerances that the advanced manufacturing type modules are, where because you're stacking modules next to each other and on top of each other, you can get out of position very quickly because there's little room to adjust. We were able to manufacture these to fairly typical construction tolerances of plus or minus 10 millimetres. And what we could do is, prior to each floor, you could resurvey the position, you could shim, you could realign, and you could make sure that things then started back in exactly the position they needed to be. It is low tech again, though. As you can see, the positioning of the modules by hand on site. It's pretty much done with conventional construction of crowbars and men pushing boxes around. That happens to be the developer client, by the way, helping push one of the very first modules into position. I was on the other corner. I think I might have been pushing the wrong way, but everyone was on deck for those first series of lifts. As I mentioned before, we're subject to very high wind loads in Darwin. And hence you need a real core. That's another one of the reasons we couldn't use a proprietary modular system, is that they just do not have enough lateral stability. So a 30-storey building, or a building this height in Darwin, has the same stability structures as about a 70-storey building in the typical East Coast cities of Melbourne. So the modules themselves are I guess, connected together by the in situ columns that lock them all together, and then they're locked back to to core and shear wall structures, which are precast, via a combination of in situ and precast corridors. Cores in Australia would typically be either jump formed or precast, with the core progressing ahead of the floors. Here we detailed the core to be able to proceed on an independent program. What that gave us the flexibility is whenever there was free crane time, if there were modules had arrived, they got put up. If there were no modules, we were putting up core or we were putting up balconies, which I'll address a little later. So the normal disadvantages, particularly in this sort of place with this sort of wind load of a highly stressed core, if you tried to do it from flat precast panels, is the difficulty of all the connectors at the corners for the structural engineers in the audience, all the junctions transferring very high shear and tensile forces. We had a crane sitting right out the front of this core, which was a 65-tonne lift crane. We could pick 38-tonne core elements up and position them on this job. So rather than go flat panels, we went to three-dimensional units, which almost eliminated all the in situ concrete construction. So just to highlight, we had two fire stairs here, which were cast as effectively a U-shaped unit, one on each end. We had a lift box as another U-shaped unit. The interstitial space between those walls was then poured in situ, but of course no formwork was required because it was only between precast panels. And then the front wall of the lifts and stairs was another panel. The only in situ wet joint we had to lock it all together was a little infill panel above the stair door on each corner. Again, sorry for the clarity here. We started off connecting these then at each floor with traditional couplers like we do on normal construction. Because the cores here are highly stressed, they are tension driven because that's the back wall of the core. It has very little load on it. It's got no floors attached to it. It's on the outside wall. It had serious tension. The couplers in Darwin, very expensive, lots of them to fit, lots and lots of laps of bars. When we had a look at it, we had core walls varying from 400 to 600 thick, and it became possible with a little bit of thought. Effectively, we've put column form tube inside the walls everywhere. What that did was it cut down the weight of the elements we were lifting because we got 200 and 250 diameter holes everywhere. But it then allowed us, rather than expensive couplers, once they were up, we just dropped conventional column reinforcement down those and concreted them and transferred all those tension forces through conventional bars and conventional laps. It turned out being a lot quicker and certainly a lot cheaper. Balconies are the other element. Unfortunately, because of the weight we already had and the size, we couldn't have the balconies already attached to the modules, so these were done as that other third activity on site. These were done as precast units as well. That's just an apartment here with two modules, and you can see the balcony slab in the front. Balconies in Darwin are very large. People live outside through a lot of the dry season. And in fact, there's a minimum planning requirement of a minimum balcony size for any apartment of 14 square metres, which is 140 square feet, thereabouts, reasonably large. This system worked with a precast floor slab, and you can see an elevation here of some of the side precast walls. They came to site with two walls and the slab already attached as a U-shaped. They were stacked up and they're tied back to the modules at the columns in the corners. Again, totally detailed and programmed so it couldn't go ahead of the modules, but it could certainly go behind, and it could go behind by 1 floor, 5 floors, 10 floors, just whatever the site logistics dictated at the time. So despite this starting with no development time, very little time to test prototypes, It did come together pretty much as anticipated. We did redesign on the run. Spent a lot of time in China dealing with an unskilled workforce over there, even down to different ways to finish concrete. Not used to fixing drywall in the way that we needed in the market and everything else. But even though they're unskilled workforce, they were very willing to learn, picked it up very quickly and worked very hard. There were some issues though, even though with those bugs we took out on the way, that we could improve on. The relatively small concrete sections, those beams are, only 250 by 300. As structural guys, we're used to designing things much bigger than that. Once you put a reinforcement cage in them, it was pretty congested. So we changed some of the detailing to make that better. Water ingress during transportation and also during construction. Those column forms, if you had a tropical rainstorm overnight when the top of a form was open, they'd fill up with water, and water under that sort of pressure finds its way into things somehow. So again, we've developed for future jobs, developed more details. And I guess the other one was too, you saw the manual labour involved in pushing those into position. We've now subsequently developed details that puts a lot more self-guiding so that they slide themselves at least to within that plus or minus 20 mil on their own in the first stage. Columns were a bit of a problem, so again, we've done some prototype work now where we're replacing the reinforcement cages with hot rolled I-section columns. They still get concreted in. It still allows us to realign and reposition, but it's going to take several hours, in fact probably a day off each floor of a similar size project. The other things we'd like to do is risers became an issue. Again, this one, plumbing risers were already defined because the things were pre-sold. They were in the middle of the unit in the bathroom. What that meant is the guys that had to come into the apartments and do final fit-off of plumbing connections through ceiling panels and whatever. When you've got fully finished apartments where the hotel rooms even arrive with the beds in and the crockery and the cutlery and everything's done, and you send a plumber in or an electrician who's got to do some work, and they drop their toolbox on the kitchen counter, they walk in with their muddy boots or whatever. So good module design has the service riser accessible always from either the corridor or the balcony so that workmen don't have to come in. Ideally you arrive on site locked up and no one goes in. As I said, a lot of this was built with an itinerant workforce, so a lot of it was Irish backpackers, and we did walk into one module one day of one of the hotel rooms to find 6 of the guys asleep on one of the beds that was already in position instead of being out on the job working. So anything you can do to keep a workforce out of a finished module is a good thing. So continued quality control is also one of the other things. Working offshore is difficult. But it did work. At the time it was finished, it was the world's tallest volumetric modular building. We have got schemes to get this similar but improved system up to about 50 levels on another site in Darwin, which again, for wind load, is about the equivalent of 100 storeys down in the southern states. And I guess the only difficulty we have now is the construction economy in that town is a little bit soft. And the other downside is since we did that one, the Australian currency is devalued 30% against the US dollar and the RMB, and it pretty much makes off-site manufacturing in China not a real economic advantage anymore. So it might be back to the drawing board for a module made in Australia. But it was a lot of fun. We solved a lot of problems, learnt a lot of things, and now just waiting for the opportunity to do one that's bigger and better. Thank you.